Hello, everyone, and welcome to our webinar reviewing the top 5 tips to achieve accurate and reliable results. Thank you so much for being here today. I'm Karen, your host for this webinar. Today, I'm joined by Jean-Baptiste Fuselier, Instron's application engineer for the EMEA market, and he's a technical expert in our low-force static systems. In his role, Jean-Baptiste leverages his trainer skills to share his know-how in accurate and reliable material testing. We expect the presentation to take about 25 minutes. Please use the Q&A section to submit your question at any time. We'll aim to address them at the end. I also wanted to mention that we are recording this webinar. You will receive an email afterwards with a link to the video, and it will also be available on our website, instron.com. With that said, I'll turn things over to Jean-Baptiste to get us started. Jean-Baptiste?
Yeah, thanks, Karen. And hi, everyone. Welcome again to this webinar where we'll cover the top 5 tips to achieve accurate and reliable results. We'll be exploring some of the most common causes of variability and unreliability in results. I'm Jean-Baptiste Fuselier, application engineer on our static product line for EMEA area. Again, feel free to ask any question in the Q&A section of the webinar. We'll take time at the end of the presentation to cover some of them. Before we start, keep in mind that before implementing any changes to your setup, please check your testing standard to make sure you are in compliance with it. So, in any given lab, there can be a multitude of factors that can influence testing results. Here we have some of the most common factors. Every detail, such as whether you are using pneumatic or wedge grips, their jaw faces, type of extensometer, and how you attach it, or what your data collection rate is, can affect your results. It is especially important to understand these factors when trying to compare results with other labs or systems. In addition to what is listed here, most labs have multiple operators running tests on multiple machines, impacting repeatability that can often be difficult to identify and thus understand how it affects your result. Every manual operation, such as closing manual grips, can have an impact. The goal of today is to go over some tips and tricks for you to feel more confident in your data. We are going to look at areas of improvement in load string setup, measurement and inputs, and finally, starting the test. You will see that each tip is common sense, but I can guarantee that if you put all of them together, it greatly improves consistency in your result. The first area to cover is setting up your load string. Setting up your equipment properly can be just as important as using the right equipment. Here we are. Our first tip is to ensure proper alignment of your specimen in your test setup. This is a small but critical detail in your testing. Factors such as jaw faces selection or operator variability can greatly affect alignment. These two things can be mitigated by choosing appropriately sized faces and ensuring alignment, either visually or with alignment devices. To demonstrate how important alignment is, let's take a look at the study we did here at Instron. In the first graph, you can see what the results looks like when little care was taken to align the specimen. The results are considerably scattered. In the bottom graph, the specimens were aligned the same every time. This resulted in significantly better repeatability, as well we increased strain and tensile strength results. Now, let's take a look at what you can do to align your specimen. The first thing that you should consider and check is whether you are using the appropriate grip faces, what we call jaw faces. Here, imagine that these gray blocks are your jaw faces and the red dog bone is your specimen. The oversized jaw faces make it difficult to easily detect misalignment. This may go unnoticed before the test begins. Moving to a more appropriately sized jaw face, the same degree of misalignment becomes a lot more pronounced. This makes it easier for your operators to detect when the specimen is misaligned. If your specimen is asymmetrical, you should also ensure that the specimen is inserted in the same orientation each time. This effect can be amplified when multiple operators are testing in a lab. Each operator tends to insert the specimen slightly differently each time, so it's important to develop a procedure which addresses alignment. When looking to ensure operator-to-operator consistency for alignment, you can use specimen alignment devices. These devices are mounted directly to both the top and bottom grip and provide a hard stopping point when inserting the specimen. This way, every operator is inserting the specimen in the same place every time. All of Instron wedge grips and our pneumatic and advanced screw side action grips can be equipped with specimen alignment devices. So if your grips looks like any of those shown here, there is an option available for you. But you don't have to buy those devices. You can get creative with this. Some customers choose to make their own alignment devices to fit on the grips. You can also even do small things like make lines on the top of your jaw faces, outlining where the specimen should fall. I take the opportunity to mention our precision specimen loader, dedicated for thin films and foils, which are really tricky to manipulate and insert in the grips. This tool helps a lot when it comes to alignment for those delicate materials. Moving on to tip 2, where we are going to take a look at system compliance. The effects of compliance are influenced by the stiffness of your frame and your load string, relative to the material you are testing and whether or not you are using extensometry. You should be sure to use the appropriate frame when testing and when necessary, use extensometry during your test. Before going into more details, let's take a look at what compliance is. Here you will see a diagram of what a test setup looks like with no load applied on the specimen. Now, when you apply load, deflection can occur in several places of your test setup, not just in your specimen. All the components of the test setup can stretch slightly. Of course, this effect is exaggerated on this photo. As a result, when trying to measure strain, the crosshead is also measuring the deflection of all components of the system, including the grips, the load cell, and the frame itself. The effects of compliance can be greater when you are testing close to the capacity of your system. So, always check that you are using an appropriate frame, as different frames have different stiffnesses. You should also check your load string to see whether there may be areas adding to compliance. Ensure that all of your lock nuts are tightened during testing. When you set up your load string, they must be tightened manually. To do that, you can use a rigid enough specimen to go to a force level above your test maximum force and lock your lock nut manually. Then unload your load string and remove this dummy specimen, and you are all set with your lock nuts. Also, other things to consider: are you using flexible versus rigid connection? Can your jaw faces shift during the test? All of these things can add to the effect of compliance. For many tests, the effect of compliance are significant enough to require the use of an extensometer. I won't go into a lot of details on all the type of extensometer shown here, but from non-contacting video to automatic contacting extensometers, there is an appropriate extensometer for every application. The important thing to understand about extensometers is that they measure the strain directly from the specimen, so eliminating the effect of compliance in your results. Many standards require the use of extensometry for this reason. Always check that you are using an appropriate extensometer for your test. Most standards dictate the accuracy of your extensometer, and every extensometer is different, so pay attention to this. And if you are not testing according to a standard, you have to evaluate if your frame and load string compliance can impact your results. While your extensometer can solve the problem of compliance, they can also introduce another variable into your setup. Like your specimen, it is critical that your extensometer is aligned during testing. In the top graph, you can see the result of a study we did, where we did not take proper precautions to align a clip-on extensometer. You can notice the variability in the modulus lines for the different specimens. Now, we can look at what happens when we ensure to attach the extensometer the same way every time. The results show much less variation in modulus results. In this particular example, on the bottom graph, we used an automatic contacting extensometer, which is called AutoX. The AutoX arms automatically get in contact with the specimen at a specified position and gauge length, eliminating the need for operators to even worry about extensometer alignment. For labs without automatic extensometry, it is critical that operators are extremely careful to align the extensometer on the specimen, both horizontally and vertically. Next, we'll take a look at what you can do when measuring your specimen to help achieve the best results. For anyone who has done testing, it can often feel like measuring the dimensions of your specimen is the most time-consuming part of the work. In many cases, it is. It also introduces a lot of areas for variability in your results. When taking measurements, everything from specimen and anvil geometry to the location of the measurement and how much pressure is applied introduce room for error. Then, the extra step of having to input the dimensions leave a lot of room for typos. It is absolutely critical that specimen measurement is done properly and consistently for your testing. I'm going to ask everyone here to use a little bit of imagination with me. Let's pretend that this red shape has a cross-section of a specimen. You'll notice that they are not flat or straight and have uneven thicknesses. You may also have specimens that have other surface defects like scratches. Let's use our imagination again and pretend that these gray shapes are the anvils, or measuring surfaces of your micrometer. You can imagine that depending on where you place the tips of on the specimen and how hard you press, you are going to see very different results. Some may take the result down the narrow section and others across the entire width. We can add to the complexity by noting that some devices, micrometers, may be equipped with spherical tips, while others may have flat tips, each resulting in a different measurement. So depending on where you take your measurement and what type of device you are using, you may artificially increase or decrease your material properties. I remind here that the stress calculated by the system is directly impacting by, for example, the width and the thickness of your specimen. Always make sure to check your standard, as some dictate both the anvil geometry and the location of measurement. Once you have figured out what device you should be using, the most important part of specimen measurement lies within consistency. Blue Hill Universal testing software can prompt users before entering specimen dimensions to ensure that they are following the correct procedure. This is what we call prompted test. You can even insert photos demonstrating where to take the measurement and which device to use to make sure operators across your lab are following the correct procedure. You can also set tolerances on your measurements. So if an operator inputs something that doesn't make sense, Blue Hill will give them an error message, forcing them to check their input. As I mentioned before, specimen measurement is often the most time-consuming part of your test. Most users are following a procedure that looks like something like this. First, they take the measurement and record them in a lab notebook or in Excel, for example. Then they will calculate an average and input this value into Blue Hill. Not only this procedure is time-consuming, but it can also introduce error if a calculation was not done correctly, or a typo was made when transposing data. For those of you looking to reduce time and errors in specimen measurement, you may consider an automatic specimen measurement device. These devices can be natively integrated into Bluehill and allows the user to input a designated number of measurements and report the average, minimum, maximum, or median by pressing a foot switch or a button. Not only it will save you up to 50% in time, it will also eliminate errors made from inputting incorrect measurements manually. So finally, we are going to look at things you can do when you have set up your load string and you have taken your measurement on your specimen. You are ready to start your test. So tip number 4. Here we will address what is probably the most common mistake we see in testing. When inserting a specimen into grips, there is often a force applied on the specimen. Depending on your material, this may be 1 Newton, 10 Newton, or even more. This force can be negative, meaning that the specimen is seeing a compressive force. You may actually see it bowing in the grips. This is usually caused by the material extruding from the grips when loading. Other times, you may see a positive force because the specimen is being put in tension. Many users are tempted to balance that out so that their tests start at 0 load. However, load should never be balanced after a specimen has been inserted in both grips. The force that the specimen is seeing is real, and balancing load will create an offset in your results. Here a test may actually be starting at 10 Newton, but if you balance load before, you are subtracting that. Don't do that. It's okay if your test is not starting at 0 force. If you are worried about this load on your specimen before starting the test, you can also use a feature that is present on our 59 and 6800 series frame called Specimen Protect. Specimen Protect works by automatically adjusting the crosshead when a specified load threshold is passed. To explain how it works, let's pretend you are running a test to crush an egg. You want the compression platens to touch the egg so they hold the egg in place, but you don't want to crush it before your test starts. So you can set your Specimen Protect to a low value, let's say 1 Newton, and drag the crosshead downward. If you jog down too far and the load starts to increase above 1 Newton, the crosshead of the system will automatically make fine adjustment upwards until the load remains below the 1 Newton value. So if you are seeing a higher values than you would like when inserting your specimen, you can set an appropriate Specimen Protect value during setup. If you don't have a 59 or 6800 series frame, you should develop a proper procedure in your lab for avoiding unwanted loads, and at least ensure that you are not balancing load improperly. Let's look at the opposite now. Sometimes, when you are loading a specimen, you can almost have the opposite effect as what we have just discussed. There can be too much slack in your specimen. Basically, it's too loose in the grips. Of course, it depends on what type of material you are testing. If this happens, the slack must be compensated for, so that your results are accurate and reliable. This can be done by a couple of different ways, which we will explore. First, let's take a look at the consequence of slack. Here you can see a typical curve of a specimen that has slack in it. Because the specimen is not taut at the beginning of the test, there is a region where load is not really increasing much, as it pulls the specimen tight. However, sometimes, you may be looking to perform a calculation early in the test. Maybe you were measuring modulus in the region between 1 and 2% of strain, something like in the region outlined here, in red. You can imagine this is not going to tell you much about your material properties, and this is not a true representation of modulus at those strain values. One way to eliminate slack is to use the preload feature in Bluehill Universal. Preload allows user to set a specified measurement value to start your test. When you hit start on the test, the system will pull or push the material at the designated speed until it reaches that specified value. Then it will balance your strain measurement and start collecting data. It is important when using preload to keep the end value low enough so that you are not eliminating any region of interest. This may take some trials to get a value that you feel comfortable with. So start low and work your way until you can see there is no region of slack in your results. It is important also that you don't test faster than your regular test during this preload step. And finally, you must remember to balance strain after preload has been reached. If you don't do this, your strain results will be incorrect. However, be careful not to balance load here. As we talked about in the last section, it will create an offset in your result. Here we can see what the graph of the same specimen would look like if preload was used. The region of the dotted yellow line is pulled before the data starts collecting, so that the graph is only showing the region of the curve you care about. And calculations performed in the region outlined in red will produce a very different result. If you did not use your preload to run your test, you can also address slack after a test is finished by performing a two-compensation, what we call slack correction in Blue Hill Universal. A slack correction looks at the beginning of the curve, finds the linear region, extends this line to the strain axis, and shifts all data to correspond with a new zero strain point. This is achieved using Blue Hill Universal slack correction found in the calculation tab of your software. If you are not sure exactly how to use this calculation or anything else in Blue Hill Universal, take a minute and to press F1 and the help file will come up. This contains a ton of useful information about what the calculations do and example on how to use them. So here we are with our 5 tips. Let's go through a quick summary. To recap, tip number 1, ensure that your specimens are aligned properly by choosing the appropriate jaw faces in terms of dimensions to be as close as possible to your specimen dimensions and use specimen alignment devices. Any other means of ensuring consistent placement of your specimen is welcome. Tip number 2, when looking to reduce the effect of compliance on your test result, take care to use proper testing equipment, both in terms of frame, load string selection, and the use of extensometry. When choosing to use extensometry, it's critical to ensure the attachment of the extensometer is aligned to produce accurate and reliable results. For tip number 3, you can ensure proper specimen measurement by following these 3 steps. First, use the appropriate device for your material, then take your measurement in consistent location on your specimens, and when looking to increase throughput to decrease errors, consider automatic specimen measurement. Tip number 4, when you are ready to start testing, make sure your load and stress results are accurate. Balance load properly. Use Specimen Protect to protect your specimen from unwanted loads during setup. And finally, tip number 5, you can use either preload before test or slack correction after test to make sure your strain result do not include slack in your specimen. If you put these 5 tips together, you can eliminate some of the most common causes of variation in your test and feel more confident in your data. I'm sure all of the information shared during this webinar will be useful to your lab and data. I'm sharing here the link to our key resources for our customers, Instron website, our YouTube channel. Aside of product information, we share application notes on testing standard, we share webinar, testing tips, Blue Hill software hints. And speaking about Blue Hill, do not hesitate to refer to the valuable embedded help of the software. It contains a lot of valuable information formatted in a user-friendly way. Last, do not hesitate to get in contact with your local Instron technical support team. We are here to help you. You might already have direct contact with them, but in case not, you can contact them through our Instron Connect portal. Here is the link. At this time, I'm going to turn it back over to Karin for some questions.
Thank you very much, Jean-Baptiste. I think everybody enjoyed this presentation. And now it's time for question. I have a question here, which came through the chat. Where can I find settings for Specimen Protect?
Okay, so settings for Specimen Protect will be inside your test method of Bluehill. I will share with you my Bluehill screen. So when you go to the method screen to configure a method in the software, whatever you are using, a tension or compression method, let's say a tension method, you can go to the tab of console. So here I'm showing Bluehill Universal, but if you are using Bluehill 3, you will have the same menus. You have to find in your test method the console environment. And in the console, then you will go to the frame menu. And inside the frame menu, you have here the parameters for specimen protection. By default, here it's configured at 3 kilonewton, but I can change the unit and set it depending on your material, as we explained, maybe to 1 Newton, okay, or to another value, depending on the type of frame and load cell you are using. So this is where you will enter your specimen protection parameter in console and frame submenu.
Okay, thank you. I have another question for you. Where can we find the settings to enter tolerances on input parameters?
Okay, so we'll go back to the method again. Well, I will show it another way. I will go to a test, So here, I'm on my test page, and it is configured to display the thickness and the width of the specimen that the operator has to enter before the test starts. And those parameters are coming from the specimen properties in the method. So if you go to the method, to the specimen tab, and the properties submenu, you will find back the width and the thickness of your specimen. And here, if I take the width, for example, by default, it's set to 10 millimeter. If I click here, I can enable some limits on this value. So let's say I put an upper limit to 10.1 millimeter and a lower limit to 9.9 millimeter. Here, I can set those tolerances on the parameter. Now, let's say I go back to my test. If I enter a value which is outside of the tolerance, let's say 10.2 millimeter, I will get a warning message telling me that it's outside the tolerances that has been defined in this test method. So yes, to put some tolerances on input parameters, I took the example of thickness and width, but everything is handled inside the specimen properties, where you can, for each of them, enter some tolerances here.
Okay. Okay, we have a third question here. Is there a way to remove compliance by software?
Yes, so this is a good question. And yes, a testing software like Bluehill has the ability to remove the compliance of your frame and load string if you are not using an extensometer. This is kind of advanced function of the software, but can be easily achieved still. Let's say we are doing a tension method again. So I'm going to a method in the software. And we'll have to use what we call a virtual measurement. So you will go to the measurement tab of the method. And inside here, you can find virtual measurements. And inside this virtual measurement, you will have what we call corrected displacement. you will add this corrected displacement to the list of active measurements in your method, and you will be able to load a compliance file. And when you will run a test with this corrected displacement, the system will subtract all the compliance from the real curve you are acquiring. But you need first to define this compliance file. To define this compliance file, you have to run a test with a rigid enough specimen that will not stretch or compress up to the load for which you want to do the testing. And you will record a curve force versus displacement, and this displacement should not move. But because you have some compliance with your frame, the displacement will change with the load with this rigid specimen. And you will save this file, and it will be your curve to correct your force and displacement data for the corrected displacement. So this can be addressed directly by contacting your Instron support if you need to address this point. But I clearly recommend here as well to use the embedded help of the software. And for example, here, I was in the measurement tab of the software. I just click the question mark here or pressed F1 on my keyboard, and it directly arrives in the measurement for the test method menu. And here, if I scroll down, I can see that I have a chapter regarding corrected displacement. So if I go through, it will explain me exactly what steps have to be done to be able to use this corrected displacement measurement.
Okay, great. Thank you. I see more questions in our chat. We still have a few minutes, of course, to answer this and try to answer this. Let me read this question. This is, if I installed AVE extensometer on a separate frame that is not fixed to the testing machine, would it influence strain measurement during fatigue tests, considering the possible vibration of the testing machine?
Yes, so when you are using whatever contacting or not contacting extensometer, like an AVE2, you have to be very careful, yes, with the vibration around your test environment that can clearly affect your measurement and data. So you have to find ways to eliminate those vibrations, such as isolation fit on your tripod, or yeah, isolation fits can be a solution to avoid those vibrations.
Okay, I hope this answers your question, actually. Another one, is it possible to conduct a system suitability test with a method in compression mode? How to proceed?
I will need to get some clarification of what exactly you expect for the system suitability test you are speaking about. But you can imagine building methods in the software, tension method or compression method, to be able to address those system suitability tests. And you would run that method, let's say, every day or every time you need to run through a specific samples. But yes, I would need to have more details on what do you want to do with this system suitability test. Yeah, but this is something you can definitively consider by creating the appropriate method.
Okay. Yes, I think this could be possible if the person who raised this question enters more information into the chat or into the Q&A section, so that maybe we can answer this question later on.
Yeah, we can get in contact with that person.
Yes.
Yeah.
Another question came through the Q&A section. How the compliance of the testing is affecting the force versus displacement in case of impact tensile tests. Crosshead displacement is higher than real displacement in case of thin soft material, such as soft plastic.
Yeah, so if you really want to evaluate, if you are not using an extensometer and you want to evaluate how the system compliance account for in your testing, you would need to run the same test methods you are running to test your material with a rigid specimen, so that this specimen, you are sure it's not stretching during your test. And you will launch the test with this rigid specimen, and you can look at the force versus displacement curve. Of course, if the specimen is rigid and should not elongate during the test, the displacement of your test should remain to 0. But you will see it will not remain to 0. And then, so you will have this force versus displacement curve, and you will see at the max force of your test what was the displacement of the crosshead with this rigid specimen. And the displacement at this max force with a rigid specimen will give you the amount of displacement which is due to compliance. So you can evaluate this number to compare to your real material under test, and looking at the displacement of your real material under test and comparing to this value, you will know if you should consider or not an extensometer, looking at the ratio between the two displacement value. And yes, this will help to know.
Great. Thank you. Thank you so much. I give a few more seconds to enter questions in the Q&A section, because I think we have gone through all of them for the time being. Well, before I wrap things up, I just have a few quick notes to mention. First, for the questions which may not be answered today or which may come up later on, please do not hesitate to contact us, and we'll make sure to answer by individual email. We will also be emailing each of you a copy of today's recording. And lastly, a survey should pop up once this webinar ends. So we'd really appreciate if you could take a moment to let us know your thoughts of today's presentation. With that said, I want to thank again Jean-Baptiste for presenting today. It was very enthusiastic and very interesting, and I hope that it brought a lot of valuable information to you. And thanks to you all for attending. We really appreciate you joining us. Enjoy the rest of the day, and goodbye.
Yeah, thanks, Karine. Thanks, everyone. Bye.